So when we write an electron configuration, when we write an address for an electron, there are 3 rules you have to follow every single time. Okay, so the way I think about it is when electrons come to check into the hotel, say I have 10 electrons and they're coming to check in, is there's a very particular way in which the clerk puts them in the rooms, and these are the rules we have to follow. The first one is the Pauli exclusion principle, which tells us each orbital, aka bunk bed, can only hold 2 electrons. Right? They're never going to put more than 2 electrons on a bunk bed, and they always have to have opposite spins. So one has to spin up, and one has to spin down. Okay? The way that we're going to draw them today is with these boxes. Chemists are very simple people. Okay, so this box right here represents one orbital, or in terms of our analogy, you could say that this represents a bunk bed. The up arrow is like on the top bunk, down arrow is on the bottom bunk. Okay? When they write things, they keep it fairly simple. Okay, second rule is known as the off-Baugh principle. Okay? The off-Baugh principle tells us that when the electrons are put into their rooms, there's a very particular order in which we put them in. It's not random. They don't just put one electron here, one there. There's a very particular order you have to follow. The way that it's designed is it's about whatever is the lowest in energy is where we want to put them. Sometimes people have said, or you call it, it's like the lazy tenant rule. Right? So if you're checking into a hotel and let's say this hotel does not have an elevator, you want to be put on the lowest floor possible. So you don't have to climb as many stairs.
No, I'm not lazy.
Most people, right?
Oh, okay.
Okay, so this means in every single atom, the first room that is filled is always the 1s because it's the lowest in energy. So if you look at this diagram here with me, so this right here shows the order of all the rooms in terms of their energy. Energy is our y-axis here. So the first room we always fill is the 1s. The next room we fill is the 2s. Then we go 2p. Then we go 3s. Then we go 3p.
Then you go 4s. 3d.
What's actually lower in energy than the 3d?
5s.
So look at the boxes. This is 3d. What's lower than it?
5s.
4s. So I think you're looking above the box.
Oh, 4s, yeah.
There you go. That's why. So 4s actually comes before. Then it goes 3d. Then what comes next?
4p.
Then it'd be
Then
4p.
5s.
5s.
Then 4d.
4d.
Then 5p.
5p.
Then 6s.
6s.
Then
5p.
Ooh.
6p.
Careful,
No,
which
4f.
one?
4f.
Yeah, so those 4f out here is actually lower. So it goes
6p.
4f, 5d, 6p,
7s.
7s,
6d.
and I'm actually missing, there should be a 7p on there. You got that order memorized? All ready to go?
Yeah, sure. Let's do that one more time. I got
Memorize.
So what I'm going to show you today is that this pattern is on your periodic table.
What the?
Yes. And I'm going to show you that today, and then that's what makes it even easier. Because I'm going to give you that when you take a test. Yeah, Mitchell.
So like, if an atom, say like an atom's like 5s or whatever, right?
Mm-hmm.
So would it have 5s and all the ones below it?
Yes.
Oh, okay.
Yep. Mm-hmm. That everything below 5s is also already filled. Yep. Okay? All right, so in our discussion today, these orbital diagrams, these boxes, okay, represent each orbital. Okay? When I have multiple orbitals in a sublevel, then we're going to connect the boxes together. Such as in a P room, there's 3 bunk beds, so you should have 3 separate boxes, but since they're all the same room, we'll draw them connected like this, okay? So this would represent like the 1s, and because of Pauli's exclusion principle, one has to go up and one has to go down. the 2s, would I connect it to this or draw a separate box?
Separate box.
Why is it separate now?
Because the 1s is lower, so the 2s is up.
Yes, different energy, so we draw a separate 2s box. Same thing, one up and one down. But then the 2p has 3 orbitals, 3 bunk beds, and we draw them connected because they're all in the same room. Okay, because I'm talking about oxygen, oxygen has a total of 8 electrons. I've placed 1, 2, 3, 4. So in this case, is the 2p room totally filled?
No.
And that's okay. We actually only have 4 electrons in there, and this is how they are positioned. And we'll explain why here in a second.
Why, so, I guess you'll explain, but yeah, why are they up and not down?
So, like these last two,
Yeah,
Yeah, because that's like saying, like, your bunk bed, like, if they want to be on the bottom level.
technically they could both be down, but our next rule tells us that they have to match. But they could both be down.
Okay.
Once again, reminder that the up arrows have a +1/2 in terms of their value, and their down arrows are -1/2.
So up is positive, down is negative.
Yep. Okay, so our third rule, which helps explain what we just saw, is Hund's rule. So this rule tells us that within a sub-level, we always place 1 electron per orbital with parallel spins before pairing them up. So the way I remember Hund's rule is you could think of it as the empty bus seat rule. Because generally speaking, when you get on a bus, if there's an empty seat or a non-empty seat, which one do most people take?
Empty seat.
The empty seat. And electrons are the same way. Is they always take the empty bunk bed before they take a paired one, if they can help it. Eventually, if the bus gets full enough, you have to pair up, right? Same thing with electrons. But if they can help it, they will never do something like this, where there's an empty bunk bed and they're paired up. This never will happen. They would much rather be spread out. And this right here is what it means by parallel spins. So like Jace brought up, technically if you wanted to draw these both down, that's fine. They just have to always match. You would never have one up and one down. Out of formality, I normally just always go up first. But if you want to be different and go down, that's fine.
Why is that? Is there a reason or just a rule?
Just the rule is that we know they have parallel spins, right? We know that because of the negative charge and things. But knowing if it's up or down, we don't know the difference. I just choose to all go up, but it doesn't matter. Okay, so now, with our electron configurations, the electron configurations are going to take into account all of the electrons in the atom. Every single one of them, okay? So obviously if I start with hydrogen, it's the easiest one to start with because how many electrons does it have? Just 1. So what we're trying to write here is we're trying to write where is that 1 electron in the atom in terms of the room and the floor. Okay? So the electron configuration for hydrogen, so write this on that line, is 1s1. And notice how I said that. It's particular here. Okay, this right here is not a mathematical operation. It's just a notation. Okay, what it represents, this first part, the 1s, this represents the energy level and the block, or the sublevel. Or in terms of our analogy, this is like saying the floor and room. What do you think the one up top is telling us? Any ideas?
That's the first room. First bed. The first bed?
Well, there's only 1 bunk bed in an S room. But that's a good point, because actually we're not going to be able to tell the difference between bunk beds here. This is actually telling me how many electrons
So like there's 1 electron in the room.
are in that room. Yep, that there's 1 electron checked into the 1s room.
In the room or in the bunk bed? Or same?
In that room, obviously in a bunk bed.
Gotcha.
Yeah. Okay. All right, let's do lithium now.
How do you know how many electrons it is?
And remember how I find the number of electrons? We're going to say they're all neutral right now. The atomic number. Yeah, just look up top. Yeah, Austin.
So for that last one,
Yeah.
say there are 3 electrons in the hydrogen atom, like in isotope.
Say that again.
Like how would you write there's 3 different electrons in one hydrogen atom? It's like an isotope.
So that would mean it's charged, right? Because isotope would mean the neutrons are changing, not the electrons. So actually, it's going to be the same as the electron configuration right now. So if hydrogen had 3 electrons, it's the same as a neutral lithium, right? The electrons are the same, right? So what's the first room? When electrons are going into the hotel, what's the first room we always put them in?
1s.
The 1s. So you write 1s. How many electrons can I put in there?
2.
2. Good. All right. So I've placed 2 of my 3 electrons. Okay? So now I still have 1 more electron that needs a room. So what's the next room I go to?
2s1.
So now I go 2s, and it's just a 1, because that's where we put it. Very good. And that's your configuration. Notice how I say it once again, that it's 1s2. You come and say 1s squared, chemists will laugh at you because you don't know what you're talking about. Okay, it's not mathematical, it's a notation. All right, let's do sulfur. I think that's the next one, right? Is that the next one on your paper?
Yes, let's do it.
Okay, so ready? Here's the light bulb moment that we're hoping for, okay? So sulfur has 16 electrons. Okay, the first thing you're always going to want to do is find where it's at on the periodic table. Okay, now here's the trick. Ready? Give me your eyes up front. If you're feeling good, that's awesome, but don't talk.
Okay.
If you read the periodic table from left to right, and then go down, left to right, that is the roadmap of what room comes next. Like so. Are you ready? So you start at the top. What room is this?
1s.
1s. How many electrons can I put in there?
2.
2. If you ever forget, count the squares. 1, 2. Okay, there's nothing else on the first row. So I go down to the second row. What's this?
2s.
2s. How many can I put in there?
2.
2. Okay, so we've done this one and this one. Now we come across, so what room comes next? 2p, and how many can fit in there? 6. So if you ever forget, count it. 1, 2, 3, 4, 5, 6. So now we have 2p6. All right, go down to the next row. What's this right here?
3s.
Now we're to 3s.
And there's 2.
2. So we've taken care of these 2.
3P.
And now we're to 3p. And how many am I going to put in that one?
4.
Why just 4, Jacob? Yeah, because sulfur, it could hold 6. But sulfur is 1, 2, 3, 4. And now we're done.
Yeah, sorry.
So make sure as you're coloring, right, that you make a little key of what each color is.
Hey, she needs that one. I'm quoting over it.
That's a weird ripple. That's not right.
That's when they say you can't have a white green without me.
If you need it, you can use it. Just need it.
For 1 second here. Okay, so after you're done coloring, what I want you to do next is with a pen or a pencil is then label each of the different sub-levels. So for example, this right here is 1s, 2s, 3s, so on and so forth. This would be 3d all the way across. And label all of your different sub-levels after you've colored them out, okay? Last thing I need to show you before we end class today, okay? So your assignment for tonight is you just need to do that front page of that homework I just passed out. Okay, so it's like 6 maybe, where you need to write, yep, that one, the electron configurations, and then it says the orbital diagrams, okay? So for nickel, you should have gotten this electron configuration. So first off, check your configuration on your notes and make sure that it matches mine, and then I'll show you how to do the orbital diagram. So the configuration for nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d8. Okay? So what an orbital diagram is an orbital diagram is just a visual representation of this. If you can do this, the orbital diagram is just turning this basically into boxes and arrows. Okay? So for example, there's a space underneath. Do you see that space on your notes? So in that space, draw out this orbital diagram so you can have one example. Okay? So we start here, just like before. For 1s, it's just going to be one box. Underneath, you want to label it as 1s. And then I need to put 2 electrons in there, and they need a 1 points up and the other points down. Something that you'll see me do when I draw my orbital diagrams is I do these half arrows. And you're welcome to do them as well. If they bug you, then you can do a full arrow. But half arrows are technically the notation for an electron, but you don't have to do it, okay? All right, 2s, do I connect it or make it separate?
Separate.
Make it separate, so draw a separate 2s box. One up, one down. For the 2p, what do I need to draw? 3 connected boxes. Because there's 3 orbitals, 3 bunk beds, but they're all in the same room for the 6 electrons we need up. Right? So then we go up, 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 and then down, down, down. Okay, carrying on, 3s. Oops. 1 box, up, down. Switch markers here.
3 separate boxes again.
Good. 3 connected boxes.
Connected boxes.
Yeah. Right? So up, 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 down, down, down. Almost there. 4s, 1 more box. 1 up, 1 down. Okay, for the D, good. We need 5 connected boxes. So even though our last orbital, even if you have boxes that are empty in the end, you still have to draw them to show that they are there in the room. Okay? So I only have 8 electrons, so first you're going to put 1 in each. So we go up, 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 up. And then we have to fill the last 3, so we go down, down, down. But even if you didn't have all of them filled, let's say you only had 1 electron in the D, you'd still have all 5 boxes and then just 1 arrow. Okay? Any questions on that? So no online assignment. All you have to do is just the front page, practicing electron configurations and orbital diagrams. Okay? That's what our quiz will be on next time.